So if you think the white dwarfs that we just learned about, with their densities of 5 tons per teaspoon, may seem incredible, wait until we learn about the neutron stars. They're stranger still. So what do you think they are? A ball of neutrons, which we already know that's whatever is left behind by a massive star supernova, or SN. All right, what supports a neutron star against gravity? Because it's a lot of mass, which means strong gravitational pull inward, is the degeneracy pressure of the neutrons this time, not electrons. Why? Because the electrons are not there anymore, right? So it's during that collapse that electrons become so close in space with the protons that they're going to interact via nuclear force, the short range strong nuclear force, and the result of that reaction are neutrons and neutrinos, but they fly away in the neutrino showers that we actually detect with the neutrino detectors. All right, so neutrinos collapse to the center of whatever it was, a star, right? So that would be this one, although you don't really see that white dot here. And here we have, this thing is the supernova remnant. Okay, the outer layers of the stars that are ejected and interact with the interstellar medium, and they're going to fade away in time. So these neutron stars, they are extremely tiny, and as we will see, they are actually the source of X-ray radiation. Okay, how small is one neutron star or a neutron star? It's pretty much about the size of a small city. So let's say Harrisonburg, Virginia. So the size of Harrisonburg, Virginia. So you're going to put in that a few 2 to 3 solar masses. So basically the whole solar system, but not one, just 2, maybe 3. You need to cram them into something of the size of a small city. And that actually ends up holding that ends up being something with a density much higher than what was amazingly high already in a white dwarf. A few words about how the first neutron star was discovered. We have discovered quite a few since Jocelyn Bell Burnell discovered one in 1967, and that was called a pulsar because there were actually a bunch of pulses, very regular pulses that were detected in a radio. She used a radio telescope. She noticed those very regular pulses, and she actually created a model and fitted the model with the observations. Those pulses were coming from a single, very concentrated region of the sky. So basically a point or a very tiny region. Okay, so this is the intensity. You see how it pulses, goes up and down, and the pulses are very regular in time, in seconds, and they're very fast as well. Some important parentheses here. Jocelyn Bell Burnell's advisor, PhD advisor, so she was a PhD student when she discovered and interpreted correctly this radio emission from what became later on a pulsar. So Jocelyn Bell Burnell's advisor gets the Nobel Prize for this discovery. One of those cases, isn't it? Yeah. All right. So this very highly it's very regular pulses and very fast pulses. Okay, they bring a really important characteristic to these neutron stars, and one of them is basically the proof that we're not dealing here with a rotating white dwarf or other things, but a neutron. Here's an example of the pulsar at the center of Crab Nebula. We've seen this supernova remnant before. Okay, so the pulses, look at that. There are about 30 pulses basically per second. Okay, so this is real observations. You see basically the intensity of that thing that is somewhere here in the center, right? Coming up and down in intensity. And here's an analogy that hopefully will help you understand better what's happening with these pulses, where they're coming from. The thing is that the neutron stars spin rapidly when they're born, and their strong magnetic fields can direct beams of radiation that sweep through space as the neutron star spins, rotate around its axis. And it's quite interesting to realize that axis of rotation does actually not align with the magnetic field, this being the axis of the magnetic field. The magnetic field that creates these beams of radiation. So that would be the direction of the magnetic field, and maybe the rotation, is a bit different then. So this would be the axis of rotation. All right. So very interestingly, there is this magnetic field that gives rise to those two beams of radiation. They're coming from the poles. Okay, and so you can imagine those beams actually acting like a lighthouse. Okay, so this is the analogy with the Earth. So this is beamed radiation. This is these are the lines of the magnetic field. You see how the axis of rotation, it's not aligned with the beamed radiation that is caused by the magnetic field. So these are some examples of how a pulsar looks like in visible wavelengths and in X-rays. All right, some just a kind of an easy to follow discussion and proof or evidence for why pulsars must be neutron stars. So remember, the evidence or the observations are actually of a pulsar, right? So what do we observe about them? We can constrain the size, okay? Basically how big that thing is that emits those beams of radiation, and that is actually very small. And from the spin rate, right, which can also be, especially for the fast pulsars, close to 1,000 cycles per second. So that is basically the inverse of the period of rotation or spinning. And so if you calculate the surface rotation velocities, remember velocity is distance per time. So basically, in this situation, the distance is how the circumference of the neutron star, and then the time would be the period, like how long it takes to travel, right? In quotes, travel along that circumference. So what do we have? The distance, 60 kilometers, times divide by time, that is multiply by the frequency, and that is about 1,000 cycles per second. So you end up with this huge velocity, 60,000 kilometers per second, which is, if you do the calculations, it's a considerable fraction of the speed of light. Remember, this is c 3 times 10 to the 1 kilometers per second. I put it here into kilometers per second. And that actually matches very well the escape velocity from a neutron star. So basically, that's such a high velocity, it would torn to pieces anything else. Also, in case you wonder about why there is such high spinning rate, well, when you start with even a slowly rotating star, when that thing collapses, right, it's going to speed up due to the conservation of angular momentum, as we talked a few chapters ago, just like it happens when the ice skater pulls in their arms. Then they spin faster and faster, and the smaller, kind of the closest to the axis of rotation everything goes, which is definitely going to be the case for the neutron stars. They're small, remember, very, very small. Okay, and they start huge, right? So that difference in the radius of rotation, that is going to be compensated by a speed of spinning that's going to increase dramatically, right? So that's why there is such a fast spinning rate for these things. Okay, so, and it's also something else that actually we can measure directly, especially, for example, for Crab Nebula. We've known that pulsar for a long time, and we measured lots of things about it. The pulsar slows down, okay? So we can measure the spinning rate the way it was like 10 years ago, and we can look at it now, or even month by month or day by day. We can actually catch in the act this giving off of energy. These observations, they match fairly well the models we have for the neutron star, the idea of that neutron star existing. So now here's the question. What do you think? Could there be neutron stars that appear as pulsars to other civilizations, but not to us? Is it yes, no, or actually there's no way to tell? And let me remind you how we actually detect those pulsars, right? So you have this thing that's rotating. There's an axis of rotation, but around it there are these beams of radiation. Okay, so the thing is rotating, and so those beams are going to appear later on like this, right? So again, the lighthouse phenomenon. And so if you actually kind of look at this neutron star from this line of sight, you will see the pulsar, right? So yes, see the pulsar. However, if this is the line of sight, you are not going to detect the pulsar, right? So basically, it depends on where that civilization is relative to us, right? So maybe this is where that other civilization is, and yes, they will see this neutron star as a pulsar, but we will not. So if Earth here, right, we're not going to be able to detect any pulsars. So actually, if we don't detect that, it's actually going to be pretty hard to say whether there is a neutron star there or not, right? Hopefully I convinced you that the right answer was that. All right. Now, there are obviously just like we've seen happen very interesting things with white dwarfs in closed binaries. Now we're going to look into what happens when we have neutron stars in closed binaries. Because we know there are stars that form in binary systems. So, eventually one of them is either going to end up as a white dwarf, or if the stars are massive, one of them is going to end up as a neutron star. And if they're close, then it's going to be mass transfer from one member of the binary system to the other. And if the one of them is going to be the neutron star and the other one is going to be some sort of a giant or a supergiant, so large, huge, therefore its surface is going to be close to the companion neutron star, then matter is going to start falling towards the neutron star. And just like it did in the case of the white dwarf, it's going to form an accretion disk. And because of the friction, because of the high speed, what's going to happen? The material, the hydrogen in particular, is heated up. And if the temperature is high, what do you think is going to happen? Hydrogen is going to fuse into helium. And because the temperatures are really high, even helium is going to fuse into carbon as well in bursts. And this is what is going to happen. It's a lot of energy, right? So every fusion process, right, that's emitting energy, actually high energy, really hot photons of short wavelength or high frequency, okay? And that ends up being in the X-ray regime, X-ray part of the electromagnetic spectrum. And for just a few seconds, there will be bursts of that kind of energy, the X-ray energy, right? So we have here the intensity of the X-ray emission for some of those pulsars. We cannot distinguish with our instruments whether that pulsar lives in a binary system, but whenever a burst like this shows up, then that is the proof that that's happened. I mean, there is no other explanation for those X-ray bursters. Okay. Another thing here to mention is that the accretion, so adding matter comes with adding angular momentum onto that neutron star, and that means the neutron star starts spinning even faster, and that's how the fastest or the millisecond pulsars, we believe, are born. Okay, just like we found out there is a limit to the mass of the white dwarf, okay, it turns out quantum mechanics has rules for the neutrons. It does not allow more than one neutron to be in the same place, the same energetic state. And so you dump matter onto the neutron star, but up to a limit, right? The gravity will win if the mass of that neutron star is greater than 3 times the mass of the sun. Okay, so some very massive stars, supernovae, can actually make black holes if enough mass falls onto the core, right? So it's not going to be a neutron star anymore. The gravity wins in crushing everything, all of the matter, into a single point known as singularity, also known as a black hole. And we will talk about that in the next lecture.